Okay, so now we go to the next item, separable Hilbert spaces. Now we are going to specialize. We are not going to consider arbitrary Hilbert spaces, we are going to consider only separable Hilbert space. First of all, let us recall what is a separable metric space. A metric space is separable if it has a countable dense set. When is a set said to be dense? A set is said to be dense if its closure is the whole space. So, a metric space is said to be separable if there is a countable set D such that D closure is the whole space. So, what is an example of a separable metric space? Any space which is countable, it is automatically separable. So, a set of integers is a separable metric space, for example, usual metric. Take the real numbers. Real numbers are uncountable, but there is a countable subset, the rationals, which are dense in reals. So, the set of real numbers is a separable metric space. Another example of separable metric space, let us take the set of all polynomials with rational coefficients. They are countable, so it is automatically separable. Let us take the set of all continuous functions on the closed interval 0, 1. Take the set of all continuous functions on the closed interval 0, 1 with sup norm. That is a complete metric space now in this case. All the continuous functions on 0, 1 with respect to the sup norm forms a complete metric space, but the Weierstrass approximation theorem tells you that the polynomials are dense. But if you take polynomials with rational coefficients, they will also be dense, because the real coefficients can be approximated by rational coefficients. Set of all polynomials with rational coefficients forms a countable dense subset of C of 0, 1. So, C of 0, 1 is separable with respect to sup norm. L2 of 0, 1 is a separable metric space. In fact, LP of 0, 1 is a separable metric space for 1 less than or equal to P strictly less than infinity. Okay, so we are given so many examples of a separable metric spaces. What is an example of an inseparable space? An example of an inseparable space, take R with a discrete metric, it is inseparable. Take L infinity of 0, 1, that is not separable. An interesting example of a metric space which is not separable is L infinity of closed interval 0, 1. Okay, so now we are going to look at a Hilbert space. A Hilbert space is first and foremost a metric space. So, a Hilbert space is separable if it is separable as a metric space. Alright. So, now take a separable Hilbert space, take a countable dense subset D1. Take a countable dense subset D1 in the Hilbert space H. Now, we have got a countable set D1. Every set, from every set, I can take a linearly independent subset D2 such that the linear span of D1 is the same as the linear span of D2. How does one do that? You have taken the countable dense set D1. If the countable dense set D1 contains a 0 element, throw it away. Delete the 0 element, it will still be countable. It will still be dense. So, I can assume without loss of generality that D1 does not contain the origin. Take a non-zero vector, take the first vector in D1, call it V1, it is non-zero. If V2 is a multiple of V1, delete V2. If V2 is not a multiple of V1, retain it. Then look at V3. If V3 is a linear combination of V1 and V2, drop V3, otherwise retain it. By this process, you are going to get a subset D2 of D1 such that D2 is also countable and the linear span of D1 is the same as the linear span of D2. Now, but now observe that the linear span of D1 obviously contains D1. So we are getting the inequality D1 contained in linear span of D2. But D1 is dense. So linear span of D2 is also dense. Okay. So now we have a linearly independent countable subset D2 such that the linear span is dense. In other words, D2 is a basis for my Hilbert space. Now all that remains is to subject D2 to the Gram-Schmitz process. Simply subject D2 to the Gram-Schmitz process, and what comes out is a set D3, which is again going to be countable. But this time D3 is going to be orthonormal, and the linear span of D2 is the same as the linear span of D3. That is a part of the Gram-Schmitz process. The Gram-Schmitz process ensures that the resulting set has the same linear span as the original set. But linear span of D2 is dense, and so the linear span of D3 is also dense. So what do we get? We have got the result that every separable Hilbert space has a countable orthonormal basis. Theorem 65 in the slide, we have just gone through the proof of this theorem. Every separable Hilbert space has a countable orthonormal basis. So classic examples are L2 of AB and L2 of R. We have already indicated for these spaces specific orthonormal basis, the Legendre polynomials and the Hermite functions. Now let us raise this question: how does one produce natural orthonormal basis for a given Hilbert space? One way is to begin with a finite dimensional setup. So when you want to answer a question like this, always go back to the finite dimensional setting and let us see what it says. Let us see what it says for Rn. Finite dimensional real Hilbert space is Rn with the usual dot product. The standard basis E1 cap, E2 cap, etc., En cap. It is an orthonormal basis for Rn. While this is a nice orthonormal basis for Rn, for a specific problem, this orthonormal basis may not be the appropriate one. What do we mean by that? Let us look at an example to illustrate what I just said. What example am I looking at? Look at the problem that is displayed in the slide. 2xy plus 2yz plus 2zx equal to 1 in R3. This equation 2xy plus 2yz plus 2zx equal to 1 is a second degree equation in 3 variables, and it represents a quadric surface. And if you replace x, y, z by minus x minus y minus z, the equation doesn't change. So this is what is called as a central quadric. The origin bisects every chord passing through it. So it's a central quadric. Which are the central quadrics that you know? The ellipsoid, the hyperboloid of one sheet, and the hyperboloid of two sheets. Now our problem is to ask what kind of a quadric is it? Is it an ellipsoid, is it a hyperboloid of one sheet, or is it a hyperboloid of two sheets? Now the problem here is that this quadric surface is not in the standard form. Had it been x squared by 2 plus y squared by 3 plus z squared by 4 equal to 1, you will immediately say it's an ellipsoid. And had it been x squared plus y squared minus z squared by 2, you will immediately say it's a hyperboloid of one sheet. Or if it is x squared minus y squared minus z squared equal to 1, you will immediately say it's a hyperboloid of two sheets. Because those quadrics that I just spelt out are the central quadrics in standard form, and so you can immediately identify it. This quadric is not in standard form. You have to use a different coordinate system. You need to use a different orthonormal basis for R3 and understand how this quadratic form looks like in the new coordinate system, namely with respect to the new orthonormal basis. So which orthonormal basis is appropriate for studying this problem? So what I am trying to say is that a specific orthonormal basis may work for one problem, it may not be appropriate for a different problem. So the choice of orthonormal basis cannot be once and for all. We have the same orthonormal basis for all problems. E1 cap, E2 cap, E3 cap will not work for all the problems. So for this particular problem, how do we go about? Let us first write this quadric in matrix notation. Let us write 2xy plus 2yz plus 2zx in matrix notation x transpose Ax, where the boldface x is a column vector with entries x, y, z. So x transpose is a row vector and x is a column vector, and A is a 3 by 3 real symmetric matrix. What is this 3 by 3 real symmetric matrix? You see that on the slide. A is the matrix 0, 1, 1, 1, 0, 1, 1, 1, 0. So multiply x transpose Ax and you will check that you get 2xy plus 2yz plus 2zx. Now we appeal to the spectral theorem. We proved the spectral theorem completely in module 5. So this course is fairly self-contained. So we appeal to the spectral theorem. What does the spectral theorem say? The spectral theorem says that a real symmetric matrix has an orthonormal basis of eigenvectors. This matrix A is real symmetric. So it has an orthonormal basis V1, V2, V3 consisting of eigenvectors of A. So let us take these orthonormal basis V1, V2, V3 and string them together to form a matrix P whose columns are these vectors. This matrix P is going to be an orthogonal matrix, and P inverse AP is going to be the diagonal matrix lambda 1, lambda 2, lambda 3 along the main diagonal. So now let us go back and put boldface x, boldface little x equal to P times capital X. Let us put little x equal to P times capital X, where P is this matrix. So what happens to x transpose Ax? It becomes capital X transpose P transpose AP capital X. But remember, P is orthogonal, so P transpose is same as P inverse, and P inverse AP is diagonal. So this equation capital X transpose P transpose AP is D and capital X. Right hand side you have got 1. What happens to this equation? How does this equation look like? It is lambda 1 capital X1 squared plus lambda 2 capital X2 squared plus lambda 3 capital X3 squared equal to 1. So now in the new coordinate system, so once you choose V1, V2, V3 as the orthonormal basis and express the quadric in terms of this orthonormal basis, the equation simplifies to lambda 1 x1 squared plus lambda 2 x2 squared plus lambda 3 x3 squared equal to 1, and you can immediately tell me whether it's an ellipsoid, hyperboloid of one sheet or hyperboloid of two sheets. All that now remains is to calculate the eigenvalues of this matrix A and find out whether all are positive, 2 are positive, or is only one positive. I leave that problem to you. That's an easy exercise in linear algebra. So we now clearly see the role played by the spectral theorem. Now we want to do a similar thing in an infinite dimensional setting. So we want to understand what avatar the spectral theorem takes in a Hilbert space. This is a very big question. In fact, the spectral theorem of an operator on a Hilbert space is a very long chapter in functional analysis. Unfortunately, we cannot do justice to this. Trying to prove the spectral theorem in generality will take us too far afield and well outside the scope of these lectures. What we need to do is to restrict ourselves to a narrow class of operators. What kind of an operators are we going to look at? We are going to look at self-adjoint compact operators on a Hilbert space. So I must define these terms. I must define what is a compact operator. I must define what is a self-adjoint operator. Where do these things come from? Why should we study compact self-adjoint operators on a Hilbert space? And why should we study the spectral theorem for a compact self-adjoint vector space? Why should we study the spectral theorem for a compact self-adjoint operator on a Hilbert space? They come from Sturm level problems which we have seen in module 5. And when you are having a Sturm level problem, we have generalized Fourier expansions in terms of the eigenfunctions of the boundary value problem. We have seen an example of this in the context of ODEs, and we have established the existence of eigenvalues and eigenfunctions using the Sturm's comparison theorem. Here we are taking a relook at the same problem but from a Hilbert space setup. So now we will go to the relevant definitions. Recall that an operator T from H to H is said to be bounded or continuous, the two words mean the same thing, if norm Tx is less than or equal to C times norm of x for all x belongs to H, where C is a constant. What does the inequality mean? Inequality means that if I take the closed unit ball, suppose I take norm x less than or equal to 1, that means I'll get norm Tx less than or equal to C. So the image of the closed unit ball U is again bounded. That means if U is the closed unit ball in H, then Tu is sitting inside the closed unit ball of radius C, capital C. Compact operators are stronger than bounded operators. Compact operators satisfy more stringent condition. That's a definition 66. Let H be a Hilbert space and operator T from H to H is said to be compact if the image Tu of the closed unit ball is pre-compact in H. When is a set in a metric space said to be pre-compact? A subset of a metric space is said to be pre-compact if its closure is compact. If its closure is compact. In other words, Tu bar is compact, and hence in particular Tu bar is closed. A compact set is closed and Tu bar is bounded. Therefore, Tu is bounded. So compact operators are also bounded automatically. So compact operators are stronger than bounded operators. If H is a finite dimensional Hilbert space, say Rn, then every linear transformation is a compact linear operator. In general, when you take an infinite dimensional Hilbert space, the class of compact operators forms a distinguished subclass of operators on a Hilbert space. And it's a very important class of operators, and they've been studied thoroughly. Now we must look at examples of compact operators. So our Hilbert space will be L2 of 0, 1. So the first example that we shall look at is the example of the Volterra operator. The Volterra operator is a very interesting operator, and we shall look at it over L2 of 0, 1. T from L2 of 0, 1 to L2 of 0, 1 given by Tf of x equal to integral 0 to x ft dt. Now remember, if a function is in L2 of 0, 1, it is automatically in L1 of 0, 1. And if a function is in L1, the integral of that function is going to be continuous. Let us try to prove this directly. In the last few lines in the slide, so let us take two elements x and y in the interval 0, 1, x less than y, and let us calculate Tfx minus Tfy. Tfx minus Tfy is what? Integral from 0 to x minus integral from 0 to y. So it will be integral from x to y. Integral from x to y ft dt mod. Take the mod inside the integral, you will get mod Tfx minus Tfy less than or equal to integral from x to y mod ft dt. Now that integral is a product of two things, integral x to y 1 times mod ft, and now we must apply the Cauchy-Schwarz inequality. Apply the Cauchy-Schwarz inequality, it will be square root of mod x minus y into norm f, the L2 norm of f. So you get mod Tfx minus Tfy less than or equal to square root of mod x minus y into norm f. not only is TF continuous, it is actually uniformly continuous. It is even Hölder continuous. It is Hölder continuous with exponent half. So the point is that this T lands up not just in L2, it actually lands up in C of 0, 1. The image of T is actually a continuous function. TF is continuous. Now, where does this Volterra operator arise? Suppose you want to solve the differential equation y double prime equal to f of x with initial conditions y of 0 equal to 0, y prime of 0 equal to 0. You simply integrate y prime equal to y prime of 0 plus integral f of t dt from 0 to x. So, when you want to solve second order ODEs, this kind of Volterra type operators will appear. Okay. So, now we shall prove the compactness of this Volterra operator. So, to establish the compactness of the Volterra operator, we assume that norm f less than or equal to 1, so that mod Tfx minus Tfy is less than or equal to mod x minus y to the power half. And this is true for all f in the unit ball. Next, Tf of 0 is 0. Why Tf of 0 is 0? Simply put x equal to 0 in this integral, you get 0. So, Tf of 0 is 0. So, when you put y equal to 0, you get mod Tfx is less than or equal to 1. So, now with these two essential ingredients, we have to show that the set Tf, where f ranges over the unit ball, is pre-compact, which means every sequence has a subsequence converging in L2. Okay. Now, to show that a subsequence converges in L2, it is enough to show that there is a subsequence converging uniformly, because uniform convergence of continuous functions on 0, 1 implies convergence in L2 norm. Remember, we have to show something is pre-compact. We are in a metric space. So, compactness is the same as sequential compactness. Every sequence has a convergent subsequence. So, what we are saying here is, since the image Tf consists of continuous functions, it is enough to show that if you pick a sequence fn's with norm less than or equal to 1, the image sequence T of fn has a convergent subsequence converging in sup norm or converging uniformly, because uniform convergence implies L2 convergence. How do I prove that there is a convergent subsequence? We appeal to a classical theorem called the Ascoli-Arzela theorem. What is the Ascoli-Arzela theorem? We shall now discuss. A family of continuous functions on the closed interval 0, 1 is said to be equicontinuous if given any epsilon greater than 0, there is a delta greater than 0 such that for all f in S, mod x minus y less than delta implies mod fx minus fy less than epsilon. Well, you may ask, how is this different from continuity? The point is, we are not discussing just one function, we are discussing a whole bunch of functions, a whole class of functions S. And for a given epsilon, the delta may change from function to function. Where is the guarantee that the same delta will work for all the functions? That is the point here. The point is, if the same delta works for all the functions simultaneously, then we say that the family is equicontinuous. Equicontinuity means that for a given epsilon greater than 0, there is a certain delta which will work for all the functions simultaneously. The next thing is that a family of continuous functions on 0, 1 is said to be uniformly bounded if there is a m positive such that mod fx is less than or equal to m for all f in the family and for all x in the interval 0, 1. So, we have got two concepts, equicontinuity and uniform boundedness. So, what does the Ascoli-Arzela theorem say? The Ascoli-Arzela theorem says that a family of continuous functions on 0, 1 is pre-compact if and only if it is equicontinuous and uniformly bounded. The proof of the Ascoli-Arzela theorem is not difficult, but slightly lengthy. It will take about a couple of lectures. We don't have time for that. So, I will give you a reference. A nice reference is Rudin's Principles of Mathematical Analysis, the third edition. If you look at chapter 7, then you will see a proof of the Ascoli-Arzela theorem, which is described in slightly general setup. What we need is the closed interval 0, 1 and continuous functions in closed interval 0, 1. Now, what have we proved? We have proved that mod tfx minus tfy less than or equal to mod x minus y to the power half. This is true for all the functions in our family. So, given any epsilon greater than 0, the same delta will obviously work. In fact, all of them are Holder continuous with the same Holder exponent and without any problem. So, if I take delta to be the square of epsilon, we are through. Look at the second display, mod tfx less than or equal to 1, that immediately shows it's uniformly bounded. So, the image functions tf as f varies over the unit ball is equicontinuous and uniformly bounded. So, by Ascoli-Arzela theorem, it is pre-compact, which means every sequence has a subsequence converging uniformly and hence converges in L2 norm, and therefore the compactness of the Volterra operator has been established. We will look at other examples soon.